So today we will start with some historical stuff about computer networks, how it was developed, and then today or maybe from next week's class, we will actually go into the application layer and study about 4 or 5 different applications, how they work, all the details, etc. So first of all, you have to understand how do devices communicate. One way of communication is through radio, okay, which does not require any sort of connected medium, it does not require any wire. However, a radio based communication is typically either uh, simplex, that is only the radio station will play the program and you will just receive it. You would not be able to send back any information. This is called simplex communication. Then it can also be half duplex. Half duplex is where one party speaks at a time, then stops, then the other party speaks, then the other party replies back. Okay. Typical example is police walkie-talkie, where or the walkie-talkie is a radio-based communication used in army and in rescue teams where you do not have a permanent communication mechanism. You can use those type of things where you say a sentence and then typically you say over to indicate that you are done saying whatever you wanted to say. Then from the other side, they say something and then again say over. Then again you say something. This means that the equipment that you have cannot act simultaneously as transmitter and receiver. It can either transmit out signal or it can receive signals that are coming in. It cannot do both at the same time. However, for the correct experience, okay, for a pleasant experience, we require actual full duplex communication. Full duplex communication is both the parties can speak at the same time if they want. It's not that we always do it. For example, right now I am speaking and all of you are silent because all of us start speaking at the same time, the class will become impossible to hold. So our communication that is happening right now is effectively a half duplex communication, but you have the option to speak, right? So this has full duplex capability, but we are using it in a half duplex mode. That's a different thing. And that's how also in telephone or mobile phone we work. Now this full duplex communication, the first fundamental example is just as I said in telephone, which came about 1878. The first telephones were set up in US in Connecticut. New Haven is the place where the Yale University is located. So my guess is that that university had some part to play also in this. Now it was through dedicated telephone switches, okay, which set up a temporary dedicated communication link between the two telephones. The two nodes of the communication link are the two telephones. One sender has to first call up the exchange. And when you call up the exchange, an operator receives your call and you tell the operator, I want to connect to this number. The operator manually, which typically in most cases, 90% of cases used to be women, the lady operator used to take a switch, a jack kind of a thing, and connect. They had socket boards in front of them. Say each socket board can handle 200 or 300 telephones. So they will take a two-ended wire with one end inserted at your end and another end will be go into your receiver. That way physically a connection will be set up and then the receiver's phone will ring. The receiver will receive the phone if available and then the two parties can talk. Later on, this human switching, this is called circuit switching. Okay, this concept is called circuit switching. This mechanism later on in the 20th century, maybe say after Second World War, say in the 50s, this process was automated, which means that, I mean, you didn't require human operators. Okay, electronic circuitry automatically at the switching offices or the so-called telephone exchanges. Why does the name exchange come? This is because this is literally a place where you perform information exchange by operators helping you to set up temporary paths. Why temporary paths? Because once your conversation is over, the operator will disconnect you from the receiver's telephone. Okay, so you have to pay only for the time you two were connected. Now, this were all made electronic, which means no human operator needed to do the this connectivity uh, in an like an manual manner. So everything was done electronically. Your phone would ring, and in that exchange, instantaneously, an electronic circuit would set up a physical connection in a switching matrix. These things, these boxes that are shown here, these are called switching matrices because they can allow connections between different parties, and it's a two-dimensional kind of a thing. Okay, from one point on the receiver side to another point, on one point in the sender side to another point in the receiver side. And once this has been set up, information exchange between the two parties is completely identical. There is no difference between who is a sender and who is a receiver because both of them can speak and send exchange information in a symmetrical way. The only difference is that usually the person who makes the call pays the money. Okay. However, mobile phones, etc., typically operate in slightly different way. At least they used to operate when in a different way when they first came up. There, the receiver also probably had to pay a smaller fee for that entire connectivity time. But nowadays, these things are going. Nowadays, you don't even need to pay any money to make a mobile call. Some companies have started. That is a different thing, but this was the basic thing. Mobile phone works in a different way. It doesn't work exactly this way. This is the simplest mode, so we are starting with this. Now, this was kind of the way in which communication happened for close to 100 years. Okay, so don't get surprised that we are teaching something completely out of date. This is out of date probably, but it's large communication, large amount of communication still happens in this way over so-called landline telephones or from mobile phone to landline telephones or from landline telephones to mobile phones where part of the communication is exactly like this. Okay, so this is still doable. And for 100, close to 100 years, this was the only option. The amount of copper wire that has been inserted all over the world to support this telephone communication, okay, is so large that you can go from Earth to the moon several times and come back, basically. The total length of the copper wire still, which is there in place, is so large. Okay. So slowly these things have been replaced by the copper wires have been replaced by fiber optics, etc. But still this wire-based connectivity was there. Now, is this good? The problem is that typically the way data is generated, both when human speakers speak, as well as when data communication happens later on between computers, okay, which are operated by human beings, it is bursty. What is bursty? Bursty means that it is irregular over time. If you plot the amount of data, the traffic volume over the duration of the call, okay, say the duration of the call is 5 minutes, okay. In this, you will find that periodically the traffic volume increases, then it falls down. When it falls down to quite low levels. For example, we typically take pauses when we speak, right? we do not speak continuously. We always speak with breaks. And in this break period, because the other party is also not speaking, the bandwidth that is there available has been made available to us by the physical connection between the two telephones is not getting used. Okay. So that there is some available bandwidth shown by this dotted line. This is the bandwidth limit. Bandwidth is the maximum rate at which you can transfer data between over a communication channel. That varies. That depends on several factors. The type of communication channel used, whether you are using wires or whether it's a wireless link or whether it's a wire, whether it's fiber optic. Okay, the type of data that you want to transmit, how that has been modulated, all these different things play a part, how noisy it is, all these different. But fundamentally, if the bandwidth is made sufficiently high so that general conversation most of the times would work perfectly fine. However, many times the peak traffic that is generated, traffic volume that is generated is beyond this bandwidth limit. And when that happens, the quality of the communication degrades. Okay, how will it degrade? Errors will be kind of come into your communication. The voice signal quality will be bad. And in computer communication, errors might accumulate. Now, you will not find these errors because the transport layer and there are many mechanisms which will filter out these errors, but it will force those information to be resent from the receiver, from the sender automatically. So that will again take up bandwidth. So because of the very nature of this bursty on off communication pattern, the bandwidth is actually underutilized. Okay, in most of the times you see the bandwidth is unused. However, when it is used periodically, it kind of overuses it. So this is kind of very unfortunate. Okay, I mean, another example is local trains, commuter trains. If you have lived near large cities like say Kolkata or Mumbai, these two are the cities that I can think of which have very large commuter population who come using by trains to their place of work. These trains during the rush hours in the morning and the rush hours in the evening are completely choked. Means there is barely even a fly can get inside. They are so crowded. But later on, later in the day or late at night or from late evening onward, when the rush is no longer there, the trains are mostly empty. So what is happening? When the demand is high among the commuted people, there isn't sufficient space for the people to travel. However, when the demand is low, trains are available, but the compartments are empty. So this is underutilization. So this is not a very good solution. The circuit switching where you set up a dedicated link and the full time this dedicated link is wasting bandwidth most of the times of this communication is not good. Then they said that, well, let us not set up dedicated links between two parties, every two parties, okay, which communicate. Let us multiplex them, okay. Let us multiplex them. How will you multiplex them? You, first of all, you digitize the data. That data digitization also, I'm hearing a noise from somebody's microphone. Could you please turn down your microphone? Thank you. Okay. First of all, digitize the information. Now, this digitization of information between the two human being cartoons that have been shown, digitization of voice, say in a telephone conversation, even in landline phones, that is an old phenomenon. Okay. This happened from about end 50s, early 60s, etc. So this was made very popular and a worldwide adopted standard called T1. The T1 digital technology standard by AT&T, the American telephone company. Okay, the specifications of T1, etc., we will not go inside them, but essentially it was a digital telephone service where analog signals generated by your voice was sampled at, I believe, a rate of about 8 kilohertz. And then it was encoded into binary and into packets, okay, with proper format. These packets can be multiplexed. You can put up identifiers on the packets and then multiplex them, and then send out the packets together over a common communication link, okay, by time multiplexing them. What is time multiplexing? You will be given only a fraction of the time, and during that time you may or may not send a packet, want to send a packet. But if you speak at other times when your data is not being transmitted, your voice will be digitized and that packet will be in hold till your time comes. And when your time comes, I think again it was at intervals of about say 0.1 second or so, every 0.1 second or so, you will be able to transmit your packet. So that packets from different people can be now multiplexed and send over a common communication link. Now, how do you decide that whose packet belongs to who? I said that put up an identifier. Actually, the classical old systems of this digital communication did not use identifiers. Identifiers is something that the modern communication systems, when we study IP addresses and IP packets, they use in the modern communication systems. So I was slightly wrong there. Sorry about that. What they did was they decided data boundaries from the communication. There are special like boundary at the boundaries. There were special bit patterns which decided that this is the start of the packet and this is the end of the packet. Okay. And because there is perfect multiplexing where each user gets a share of the time of like in fixed intervals, they get the access to the communication channel. There is no possibility usually that two packets will collide from the two users because they will kind of be taken at periodic intervals. Okay. Now you see the communication channel utilization looks much better. Okay. There is barely any time the communication channel is empty. So this is called packet multiplexing. Now, coming to computer networking. Still, this is not probably networking. We have just discussed a basic mechanism by which packets can be multiplexed. Packets, a digital collection of data, can be multiplexed and sent over common communication link. Now, DARPA, or Defense Advanced Research Projects Agency, is an US defense funded, US government defense department funded agency which periodically puts out research proposals, calls for research proposals. People submit research proposals in response to these calls and DARPA funds this research. DARPA funds this research in government laboratories, in universities, and also in companies. Okay, so it's a competitive thing. Now this Robert Taylor, this gentleman was he became the head of the information processing office at DARPA in 1966. Now he wanted to realize an idea of an interconnected networking system where computers could interconnect and exchange data with each other. I believe the first working prototype of this was developed not in USA but in UK. This Robert Taylor gentleman And there was this name Licklider. Licklider actually was probably involved in that effort in UK. Robert Taylor, this person visited a conference in which he attended a presentation of a paper where this interconnected computer concept was described. And Robert Taylor decided while going back to US, he felt a little scared because this was a time 1966. These were times when the Cold War between USA and Soviet Union was at a very high tempo. Okay, so everybody was scared anytime huge war will break out. Okay, so and this USA and Soviet Union wanted to beat the other in different technological aspects. Now this Robert Taylor, immediately when he saw this, he decided that he must do something to develop similar infrastructure in US. And then he got people from different big universities like MIT and UCLA and Stanford Research Institute, SRI, part of Stanford. And in UCLA, I believe the main professor who was involved is called Leonard Kleinrock. He's a very famous queuing theorist. What is queuing theory? Later on, maybe we'll just touch upon. Queuing theory is the statistical analysis of this packets about and how much delay is required for the packets to transmit in a finite bandwidth mechanism, etc., etc. Okay. So, anyways, so this Kleinrock's name is mentioned. So they wanted communication between UCLA and SRI, and basically they wanted to type the word login. Okay, LOGIN. So around 20 to 30 hours on October 29, 1969, they said we typed an L and we asked on the phone, have you received? They said yes. Then you say O and they, did you see the O? They said yes, we see the O. So L and O were transmitted, considered a chatting system, okay, in modern technology. Whatever your friend types on this side, that gets reflected on the other side. But usually you don't need to confirm immediately with a live phone call with your friend that, yeah, can you see what I'm typing? That is not required. But the reliability was not there in this first network that was set up between two computers. So they were also connected on a phone, which was much more reliable at that time. And they were verifying whether the receiver was receiving. Then they typed the G and the system crashed. So L and O were the first letters that were transmitted. Okay. So by December 1969, 4-node network was connected by adding University of Utah and University of California, Santa Barbara, UCSB. So in 1969, if you call this a network connectivity graph, the entire network connectivity graph consisted of only 4 nodes. And these 4 nodes were not physically connected with each other. So this is not like a complete graph where every node is connected with every other node. For example, if you look at it, Utah is only connected to SRI, but not directly to UCSB and UCLA. This is a very important feature. Okay. So this is a fundamental feature that all node would not be connected to every other node physically. If they want to communicate with a node with which it is not connected directly, they will route the information through possibly another node to which it is connected. So if Utah wants to send a packet to either UCSB or UCLA, it has to go through SRI. This is a feature which we also described in the last class. The reason is if there are n nodes in a graph and you choose pairs of them and decide that they will be physically connected with each other, you are going to have order n square connectivities. This much of connectivity, order n square connectivity, is not possible to sustain if n as n starts getting larger. Okay, so this issue has been actually described in nicely in the book by Tannenbaum. This picture is also, I believe, taken from the Tannenbaum book. By the way, this net was called the Arpanet. Okay, so this was the first packet switch network. Then USA is a very huge country. Okay, so by 1970, they had set up this connection with the East Coast. Whatever was happening in 1969 was in the West Coast. And in 1970, they were set up stuff in the East Coast. That means that they had to set up or utilize the existing telephone connection from East to West. That time, like a wire-based telephone connection from East to West to do this thing. Nowadays, you have instant connectivity, whatever is the distance between the two telephones. In mobile phone, you just dial your friend's number. Your friend might be located thousands of kilometers away. This was not the situation even say, I would say probably late 80s or early 90s or so, late 80s. So why do our mobile phone this thing work so fast, or distance does not matter, because the communication is largely handled by satellites. Beyond up to a point, it is handled by your mobile phone tower and then maybe a wire connection. But beyond a certain point, it is connected by satellite connectivity, to which distance on the ground does not matter. Okay, so but this infrastructure that we are talking of is completely copper wire connection based. Even fiber optics had not come. So if you wanted to call somebody at a large distance away, these copper wires were very highly utilized between the long distance cities. For example, you want to call from, say, New York in the east to, say, uh, Los Angeles in the west, in US, in the US context. You had to book a trunk call. Means you had to say that I want to place a call, and for that you have to book in advance, because many people were trying to use the same connectivity link between New York and Los Angeles. So many people were trying to use that, even by multiplexing that cannot be handled. So you had to book a long distance call in advance, and then they will say that, okay, you can now make a call whenever your time comes. Even in India, that was the case. This stopped when the STD direct dialing facility started. I believe, I don't know when it started, probably late 80s or sometime in the 80s, where you could directly just type a number, like type your number, and then wherever is the city the other receiver phone is, you could directly call. Now this network that was being set up, it also had several other features, desirable features. So it had to be efficient. It had to be fault tolerant. Fault tolerant in a sense that if these were copper wire based connectivity, okay, if one of the connections get lost, I mean somehow it gets damaged, then still communication will be possible by routing through the other connected nodes. For example, in the communication graph shown in 1970, Utah has two connections, one to the west and one to the east. Now, if both of these connections get damaged, then yes, Utah will completely get disconnected from the rest of the graph. But both of them will get damaged at the same time is probably not very practical thing. So say if one gets damaged, Utah will still have access to the rest of the graph through other nodes. So that's a very, very important fault tolerant feature of this network. Remember, this was designed by defense, okay, by the defense agency. They always had to keep in mind that if there is a war and communication links, telephone links, long distance telephone links get damaged, these long distance telephone links were called trunks. That's why the name trunk call had come. If these long distance telephone links get damaged, then this network should have some inherent capability to still be alive. Okay. Then there are other things were required, that there should be error correction, because the telephone wires are, it's okay, but they're not the best conductors, okay, of high speed electrical signals, especially if the sending data rate increases very much. Okay, at that time the data rates were in the order of kilobyte per second. Now Ethernet supports, theoretically supports 1 gigabit per second, and 10 to 2 standards are there, 1 gigabit per second and 10 gigabit per second. So you can imagine the difference in speed, like 10 to the power 6 difference in speed of data transfer rates that has happened. But within 1977, a large network had grown. Okay, so it spread quite fast, and for a long time, Arpanet was the largest computer network in the world, operational computer network in the world. So there are some nice YouTube videos, general videos on computer networks, how it developed. There are some nice textual information also. All of you can read this. It's very fascinating. Now let us come back to a modern computer network where the network functionality is provided by the protocol stack. Okay. At the end, at the bottommost layer is the physical layer where electrical signal values, voltage levels, how they are modulated, what is the definition of logic 0 and what is the definition of logic 1. This type of fundamental things are discussed. You might be surprised to know that 0 volt is logic 0 and some VDD volt, say plus 5 volt is logic 1. This is not the only solution of this problem. In fact, if you follow this 0 and VDD, the common convention for to describe logic levels for while converting them to voltage levels and transmitting them over the copper wires, it creates lots of problems. So lots of tricks are played in this to encode logic 0 and logic 1 values in slightly different manner. For example, it might happen that, say, it can be a bipolar encoding, which means that, say, logic 1 is plus 5 volt and logic 0 is minus 5 volt. This is one possibility. And there are many other ways why these complicated encodings are done, etc. is a subject of digital communication, and we will not go into them. Unfortunately, this is a very fascinating subject, but probably will not have time to go into them. One of the important things is that other than the physical layer, all the other layers require considerable amount of software, and the amount of software requirement increases as you go towards the top. The application layer is kind of entirely software. The transport layer is also entirely software combined with some, well, some basic probably help from the operating system, etc. And the network layer is software combined with high-speed specialized hardware. The data link layer is probably mostly hardware, but still software is there. Data link layer, most of the task is performed by hardware, because the data link layer has to operate at very fast speed, and the physical layer is probably completely hardware. So anyway, it's a nice mixture of hardware and software. So the software has to be developed. Okay, now all modern operating systems kernels have this whatever amount of networking software that is required for the network to support the transport layer and the network layer functionalities inbuilt into them. All modern operating system kernel, like I am right now talking to you from using Windows 10. Okay, maybe in lab or office for some serious work, I use Linux. Most of you use Linux. Okay, maybe some of you use Mac, OS X. So all these modern operating systems have the networking functionality, protocol stack, software inbuilt into the kernel. You don't need to separately do this. This was not the case. This started happening from about, I believe, sometime in the late 70s, the versions of Unix that came out, or maybe I think the early 80s versions of Unix that came out, that started having the TCP/IP support inbuilt into itself. Okay, this was not always the case. And by the way, Unix and Linux are different. Okay, Linux was supposed to be a clone of Unix, which can be run on relatively low-end personal computers. Okay, and Unix was not free, other than some versions of Unix which were made by universities, for example, BSD, Berkeley Unix, Berkeley Standard Distribution, and so. Linux was supposed to be a clone of Unix, very similar in the commands, etc., but should run on personal computers or PCs. Okay, the DOS operating system was a clone of Unix, again supposed to run on personal mini computers, which were brought out by IBM. The word personal computer itself is an IBM word. Okay, it was introduced by IBM. Anyways, so we don't need to write software on our own to make our computer support networking functionalities. That's a very important advantage. Okay. You can of course write application, you can develop new applications using the network functionalities provided by your operating system using API calls. There are many funny stories about the initial days of software development. I believe one of the stories was something like this, that the time at which this 1969, when this network Arpanet was coming up, they called for some bright PhD students from different universities together for a conference. The PhD students went there and they said, okay, this is the specification. Okay, please write the software. And when the PhD students went there, they thought that the software is already there and they will be asked to change small parts of it. But the PhD students, I mean, very young PhD students were astonished when they were told that there is no software. Nobody knows how to write software for some interconnected computers or to connect computers. So they wrote software on their own within a few months and set up this first 4-node or 3-node the computer network, Arpanet network with a 3 or 4-node network. Transferring software once you have written it was a major pain, because try to understand, there was no way, there is no network. Okay, there is no computer network, there is no email. Okay, how will you transfer the data, that the software that you have developed, to the other party, to your collaborator? The only way it was to actually store it on a magnetic disk or something, and then to physically post it. Okay, so that was the only option, so that the receiver would receive it in the magnetic disk or floppy disks. It's a floppy disk, I believe, came even later, probably early 80s or late 70s. Magnetic disks or tapes, okay, which look like this long this movie, old movie discs. They had these long tapes from which movies used to be played. similar kind of stuff, and then you had to post it, okay, or physically transport it by a car or whatever to your collaborator, and then you could have the software. So there are many funny stories about the software development because nobody knew anything. Okay, what is going on was completely a novelty. Say for example, somebody now, those of you who have by now you are in third year, second semester, by now you have developed considerable software in whatever programming language, C, Java, Python, C Sharp, whatever is your choice. Say somebody tells you that I want to develop, say, a software that is going to play movies, okay, a movie player software. You will first search for similar code on GitHub or places like that where people have done similar projects and have released their code. And then you might take that as a starting point. And then maybe you would modify that code, add extra functionalities, change the GUI as per your liking, add the functionalities that you want, etc. to have something. But at least you know what is a movie player. What is a software? Say the VLC is a very common media player, right? You know what is a media player software that can play different types of files. There at that point of time, nobody knew what do you want, there was only a list of specifications that these have to be supported. Other than that, there was nothing. So it was very challenging actually to develop software. Then later on, DARPA gave large contracts to the leading corporations at that time. They also miserably failed sometimes to develop the software, and most of the software was developed by very bright students at primarily two universities. One is Berkeley and the other is Stanford in US. So they developed most of the software. Now let us now understand the different services provided by the different layers. Okay. First is the transport layer service. It creates a possibility of a connection oriented communication. Means your Carnot is connection oriented. Your machine, the two machines on the two sides, they maintain information about the communication. They maintain, this is called, they maintain state information about the connectivity. They maintain state. And for every such connectivity, they maintain the state. So here the diagram shows that somebody, a computer from an arbitrary person, is trying to connect over the internet to a server located at google.org. Could have been google.com also, but what is the difference between org and com, etc.? When we study DNS, probably next week, we will come to know. But anyways, somebody is trying to join to a Google server, computer in Google. Point is the Google server is probably not serving only you. It is serving millions and millions of people all over the world. So for each of these connections, it maintains a state information that yes, this connection has been set up. This is a logical connection between you and your machine and the Google server. Why logical connection? There is no physical wire link. The physical wire link is only from the start of your machine to some place where this wire ends, and then the routers begin, and similarly from in Google where the router begins in their office and up to that machine, there might be a wire based connection. Other than that, in between, it can be wired, but it is slightly vague exactly how this connection is happening. TCP does not bother about how this connection is happening. Okay, because this actual connectivity is maintained. There is no actual connectivity, real-time connectivity. You think that you have a dedicated link between these two machines. You are typing something or using your keyboard at your machine, and the connection lets you see that those are being typed in the say email body, which, and you then press like a send or something, that email is sent. You are typing something in your browser locally, but that gets synced and reflected in Google. Later on, you will understand and we will see that this is actually more than a connection between a human being and a server on the other side. This is actually a connection between two processes. What is a process? From operating system, you will know that a process is a program in execution is called a process. Okay. So in computer science terminology, this what is happening is two processes are communicating with each other. Okay. Your computer doesn't know that you are sitting at the keyboard and typing things. What your computer maintains is a operating system maintains is a process. It supports the process by providing whatever resources it needs, just like any operating system does. And it maintains the identifiers and all information necessary to create a logical connection between your machine and the remote machine, to maintain the logical connection over time, to send out information, to receive information and pass on to your process, to take information from your process, make them proper packet out of it. There are many specifications. You cannot send out information in arbitrary way when you are following a protocol like TCP. Okay, that's why they are protocols. Protocols means there is a rule for everything. Okay, so whatever you are typing will be made into packets. Those will be taken from your process corresponding to where you are typing your stuff. They will be made into packets. They will be sent out from your computer and they will travel magically over the internet and reach the destination magically, whatever distance it is at, after some time. And there the receiving process will receive the information because your operating system will strip down that packet and extract the information for you from those packets which is relevant to your application, to you, the process at Google server, and it will pass on that information to the Google server. In this way, this thing happens very fast, and this thing happens very fast repeatedly over the entire duration of the communication. And it is guaranteed that there will not even a single bit will be in error based on whatever you have sent and whatever is being received at Google and vice versa. When stuff is being sent from Google and coming to your computer, that will also not, one bit will not be corrupt. It might be corrupted, but your process will get the absolutely pure information. Your processes will not face any corrupted information. This is the difference is very important to understand. See, on the way, the information might get corrupted, but somehow magically the software transport layer protocol will ensure, by being at the gatekeepers at the boundaries, that your processes will not get something nasty. So as if they will check at the boundary, the stuff that is coming in, is it okay? Does it have any error or not? If there is an error, it will tell the other side, look, I will not receive this packet. This is in error. Please give me, resend the correct error-free packet. Only then I will if I receive it error-free way, I will transmit it to the process at my end. It is slightly similar to, say, all of us probably nowadays, especially given this COVID situation, we are buying stuff from online stores, right? Like Amazon, Flipkart, etc. All of you probably have been doing it for a long time. Now, sometimes on the packets, it is written that if you find the packet is damaged, Do not accept it. Just return it to the delivery man saying that this package is damaged and then we'll take care of it. It is kind of similar. So your transport layer service at any computer, either the source or the destination, will not accept nonsense corrupted stuff. It will reject it. Now, how does it detect there is corruption in the stuff packet? Well, it uses error corrections and that will study. Similarly, the transport layer services ensure that there are no missing packets. For example, as I said, that all information cannot be sent in one packet. They are broken up, made into multiple packets and sent. Say you are typing, my name is XYZ. Okay. Now my was formed in a packet, name is was formed in another packet, and XYZ is another packet. Now all these packets are serially numbered 1, 2, 3, etc. Say packet number 1 contains my, and that gets properly delivered at the receiver. Name is packet number 2. Somehow on the way it gets lost and it is not delivered. But the receiver has no way of knowing that on the long path between it and the sender, it has got lost. There is no way of knowing actually. Now, packet number 3, when it comes, the sender will see that it is expecting packet number 2 because the receiver. The receiver keeps track that next, till now I have received 1, next packet should be number 2. Now, instead of 2, when it receives 3, it tells back the sender. It does not receive the packet. It says 3 and says, no, this is not the correct packet. Something is missing. And it tells back the sender that please resend back 2. Because I have not received 2. Maybe you have sent 2, but I have not received it. And I will not receive 3. Or maybe I will receive 3, but I will not deliver it to my process until you give me 2. So there might be 2 options. One is your receiver will not even receive 3. After 1, until it receives 2, it will receive nothing. And the other option is it will receive 3, keep it stored locally in a buffer. When it receives 2 finally from the sender, then 2 and 3 together, it will pass on to the application or process. All these details we will study when we study the transport layer. Okay, it is quite fascinating stuff. How do I identify processes? TCP will identify processes using something called port numbers. So that's a different concept. Port numbers are identifiers that are connected with processes. Now Unix or any Unix type operating system like Linux uses small integers as identifiers of processes called process IDs, PIDs. Okay, you can type a ps-u command -u username and see all the process IDs of your currently running commands, or you may type the top command and see the process IDs. These process these identifiers for processes are slightly different from the port numbers. They are connected to processes using special API calls. You will study this later on. And that interface is called a socket interface. Those of you who will be in the lab will study that in detail. The process to process connection is bidirectional. Okay, so unlike the walkie-talkie example I was giving, that simplex half duplex communication where only one side can send at a time and the other side cannot. It is until it receives the thing, it cannot send. It's not like that. Anybody can send anything at any time and receive anything at any time. Okay. So this is full duplex communication. By the way, not all communications, even in computer networking, are inherently full duplex. I think we will study examples where the links are actually simplex, which means that only from in one direction data transmission is possible. And if you want bidirectional data transfer, you have to set up two simplex connections, one from point A to B and another from point B to A. Only then you will can perform bidirectional data transfer. Why this is done? Well, it is more difficult to implement full duplex communication in software and also in hardware probably. Okay, that is why a walkie-talkie set, a radio set where you can both hear and speak is much more complicated than a radio set. In a radio set, you are not expected to speak. You are only supposed to hear, listen to music or commentary of sports or whatever news or whatever is being transmitted from the radio station. And you have to be happy with that. You have no say on what the radio station is going to do because you cannot give any feedback back to the radio station using your radio set. So that is simplex communication. Okay. But full-fledged radio receiver is receiver cum transmitter, like in walkie-talkie or similar stuff. That is much more complicated because you also have to send out signals, right? So that also requires larger batteries because sending out signals is a massively power hungry operation. The typical radio stations that we use in any big city, typically their transmitters are in the order of megawatts. So maybe 1 megawatt transmitter. Okay, that's massive amount of power will be required. So transport layer provides connection-oriented communication. It creates a logical connection between your machine and Google server and remembers the entire connection state over the entire span of communication. It ensures ordered delivery of data packets. It ensures perfect reliability. Okay, no loss of data packet is allowed. No error in data packet is allowed. It performs flow control so that the sender cannot overwhelm the receiver by sending too much data very fast, and it avoids congestion in the overall network by detecting when congestion is happening, and then by its own it is trying to control the congestion. This last point will be slightly difficult for you to understand right now, but I'll just try to give an example. See this in this diagram, this blue cloud kind of thing that has been shown. This is probably a shared channel used by many different communicating computers. Okay, all of them are pumping in data into this this medium. Okay, at the same time, this medium has very high bandwidth, but still it has finite bandwidth. Bandwidth cannot be magically increased. Okay. So if everybody misbehaves and tries pushing in data at arbitrary rates into this, everybody else's performance will suffer. Other than the receivers will be in big trouble trying to process data being sent to the receiver at such high speed. In a shared medium, you will disturb others also. So that's an undesirable, what should I say, undesirable consequence of sharing a medium. Okay, say for example, you are quarreling with your friend over phone. Okay, you are shouting over phone, and your friend would not be able to hear what exactly you are saying because you are shouting. And say if you are in a crowded environment where other people are also present, they would also not be able to hear what they were talking among themselves. So suppose there are two other people in the room talking among themselves, their communication would also be disturbed. It's not really that you wanted to disturb them intentionally. Just because they are in the same room, unfortunately, at that point of time, their communication would also be disturbed because there is a shared medium of communication. So this is a big problem, And because everybody, it's a distributed internet is a distributed environment where there is no central control over the senders and receivers. This is the fundamental simple principle of congestion avoidance. The moral of the story is that in the absence of a headmaster or a principal who will scold the boys and keep the class silent, or the class teacher or will come when everybody is shouting in class and say, hey, be quiet. In the absence of such an authority, it is the responsibility of the individuals to behave themselves. Okay. So when the individuals through their own experience see that data communication is getting very, the performance is becoming really bad, it is becoming very noisy. I am not receiving my packets within expected duration of time. I'm not receiving my packets in order. The performance quality is degrading a lot. Okay. It behaves itself. It says that, well, I have to understand that the network is in right now the network is not in good shape. So let me do my part. Let me behave myself. Let me not send out data that fast. And it hopes that everybody else will also have this good sense of behaving themselves individually. And when good sense will prevail among all the individuals, then the entire network within a short span of time will also start behaving much better compared to earlier. Okay. So this is the fundamental moral of the story, that if the agents involved in the communication simultaneously find that the communication quality is not good, there are ways to estimate how communication quality has degraded. Okay, that it continuously estimates. Any communicating entity will continuously evaluate what is the quality of the current communication. Just like when you see a YouTube video, automatically the video frame rate might change depending on the available bandwidth. The same video one day you might watch at full resolution, on other day automatically it will be shown to you at a lower resolution, because your browser and the associated software has determined that currently the network bandwidth available and the network performance is not that good. So what it will say, okay, I will behave myself. I will not put extra load on the network. Rather, I will just affect the viewing experience of the viewer by projecting a lower resolution video will require lower transmission bandwidth. And as a result, my load that I was putting on the network will decrease. If similar thing happens with all the people watching YouTube in the network, for everybody the good sense prevails, then everybody's demand on the network will be less. And as a result, the network will very soon become well behaved. Now, that might raise a question, but then everybody, when it becomes well behaved and that performance again goes back to good, everybody will start watching videos at full resolution. Again, the network will face problem. Yes, those type of things might happen, but there are ways to resolve these things. Okay. We'll study some of them. So flow control and congestion avoidance are probably the two most complicated features of transport layer services, which we will study. Then is the network or internet layer services. Okay, this is quite peculiar. Okay, they take the packets from the transport layer and constitute something called datagrams. Okay, which is also, people say IP packets all the time, but they should actually be called IP datagrams. Okay, they construct something called datagrams, which are kind of larger packets, data packets, and route them to the next router, next hop. Okay. Now, why do transport layer packets need to be converted to datagrams? Because extra information is needed, and there are extra options that are needed between routers to add this routing information, etc. Because the transport layer does not bother about how this transport layer only knows about destination and source and destination. It doesn't bother in between what the hell is happening. But the network layer has every stage it has to reside up to this point, then which point, finally till the destination, like this. So it has to add additional information, and so the transport layer packets have to be converted to IP datagrams. Although later on we will keep on saying IP packets all the time, the correct terminology is IP datagram. It uses an identifier called IP address to uniquely identify a host in the network. Ideally, every host in the network has an unique IP address. Unfortunately, that does not hold. The modern IP addresses are 32 bits. There is a proposal to increase them to 64 bits or 128, whatever, IPv6, but it is still not implemented widely. 128 bits, I think, is the proposal, but so the version that we will study is called IPv4, IP version 4, that is a 32-bit address. We will study this in very, very detail later on. Okay, what is the meaning of a 32-bit address? Unfortunately, every node with 32-bit addresses, the number of nodes, the number of connected devices in the world have become so large that you cannot keep on using, you cannot have unique IP addresses for every computer or every device. Remember, your smartphone is also a network device, right? It also has an IP address. So it's not really possible to have, there's so many smartphones, so many computers, so many servers, so many everything. Okay, smart watches, these, that, everything needs an IP address. So it's quite difficult. So how to have smaller IP addresses to avoid, I mean, how to have smaller number of IP addresses and more number of clients, so that to support more number of network nodes, so that there is effectively no clash. Well, many tricks are played, and some of these tricks we will study. That how does virtually it makes it look like every node has a unique IP address where it actually doesn't. Okay, there is something called network address translation and all these things, NAT. Okay, when you have been inside the IIT campus, you have seen proxy server addresses to be 172 dot something. These addresses starting with 172 or 10 dot something, these are special addresses. You will not find this type of IP addresses on the general internet. You will only find it inside an intranet or an internal network. Okay, all these things we will study. So it performs host addresses, it performs connectionless communication. Connectionless communication, the first point is also peculiar, because just like the transport layer maintains state information about the sender and destination, network layer does not maintain any state information. To it, all packets from different agents passing through a router all are the same. It gives no preference to anybody. It just receives packets and forwards it through its proper interface out to the outside world, depending on certain metric or information available to it. This is called routing, and through the collective effort of all the routers between the sender and the receiver, finally the entire datagram is routed to decide the path to from the source to the destination node in the network graph. Now, data link layer service. Further, the network layer data packets or datagrams are now formed into even larger packets called frames. It performs frame synchronization, error control, flow control, okay, at channel access or medium access in a shared channel, and then it needs to perform physical addressing so that these network addresses are transformed from a network address to the physical address. These physical addresses are called MAC addresses. Okay, so these are 48-bit quantities, and these are guaranteed to be unique for every network device around the world. The data link, I'm just passing through them quickly because you will not remember everything right now. If I just go into the detail of each of these functionalities. However, one thing you should remember is that the data link layer is actually broken up into two different sub-layers. One is called the logical link control, or LLC, which performs error control and flow control. And the other is called medium access control, or MAC. Okay, so which allows multiple communication agents to share a channel. So the physical address is the MAC address, and the logical address is the IP address. Okay, the logical address is used to find out the path towards the host by the network layer, by the network routers, and the physical address or MAC address is used by the data link layer to finally deliver the data packet to that person. Okay, for example, say one possibility is that Professor Sandip Chakraborty sits in room number 311 of the CSE department of IIT Kharagpur. Okay, so this is a logical address. This might be a temporary identifier because the logical address or the IP address of a network node might change over time. In fact, there is something called DHCP, which typically assigns temporary IP addresses to devices. Say you are carrying a laptop in your bag. At the end of class, you open the laptop, you connect to the internet for 5 minutes till the next teacher comes. So at that point of time, your laptop needs an IP address. Okay, so that IP address is within a few microseconds is kind of given to you by the Wi-Fi connection to which you connect. Okay, through a process called DHCP. Now, next, in the teacher comes, you close down your laptop. Again, after 1 hour, you open your laptop. At that point of time, your IP address may or may not be the same IP address that you had 1 hour back. May or may not be. In that case, if a new IP address is required, again DHCP will give you a new IP address. Okay. And cases where this IP address do not change are called static IPs. Say, for example, every faculty room computer that is there in the faculty rooms in the CSE department, every faculty room computer has a static IP address that does not change over time. Okay, but that is very, very rare. Usually in a network, static IP addresses are much, much rare. Probably DHCP addresses are much more common. And this can change over time. But physical address is say the Aadhaar number or the PAN card number of that individual. That will not change in his entire lifetime. Okay, that uniquely identifies the individual. There is guaranteed that it will not happen. Another person later on will have the same identifier, same Aadhaar number, or same PAN card number. That is impossible to happen. That will not happen. Okay, that's why PAN, permanent account number. Why is called PAN, permanent account number? It will not change in your lifetime. Okay, so this is kind of an analogy between the two different concepts of logical address and physical address. The MAC addresses, as I said, are 48-bit numbers, which uniquely identifies every network card actually. So it might happen that there are multiple network cards in a device, and in that case, the device might have multiple MAC addresses, 2 MAC addresses for the same device, because the network cards have different MAC addresses. Okay, sorry, 64-bit. 64-bit MAC addresses are shown, but I think it is 48-bit also. But anyways, so logical addresses and MAC addresses are typically written using this notation. For the logical address, hex notation is also allowed, but most commonly they are written using decimal notation, like 172.16.62.64. What is the meaning of these dots? What is the special meaning of the starting part 172? All these things we will study in great detail. Whereas the 64-bit MAC addresses, if you have, they would typically be written in hex, where each two nibbles, that is each 8 bits, are separated from each other using colon, like shown here. Okay. So in a host operating system, the physical layer is implemented primarily in hardware. The firmware and device driver is kind of shared between the physical layer and the data link layer. Those are also probably operating system stuff. Sometimes they are part of the operating system kernel itself. Sometimes they are add-ons which you need to install later on as and when required for new devices. Then there is a network layer and transport layer, and these are implemented typically mostly by the kernel software already available, and they are also, you can also write your own software at these layers and do stuff, and the application is entirely software. That is that is up to you. That's not an essential component of your host. Of course, to use the system you require some sort of application mostly, but it's not an essential component. So how does application layer data pass through different layers? Well, say for example HTTP data, the type of data you use all the time to connect to websites. So you have an HTTP data and HTTP header. Then when it goes to the transport layer, a TCP header is added. Then when it goes to the network layer, an IP header is added. Then when it goes to the data link layer, a MAC layer header is added. And finally, when it goes to the physical layer, a physical header and a physical trailer are added. So in this way, the amount of HTTP data that is there, that has remained actual data that matters, that has remained constant over the entire collection of data packets, but it has kept on increasing in total length. And unfortunately, the physical layer at the bottom typically has a limit on the maximum total length of a packet that it can support. It is around 1500 bytes at current technology, which means that you have to now back calculate to find out the maximum amount of HTTP data that can be generated from your application that can be this is called encapsulation of data into larger packets. Okay. Maximum amount of data, length of data that can be encapsulated in a larger packet. Okay. So, well, I think I made a mistake. The 1500 byte limit is, I'll just check. I think either the physical layer total length is about 1500 bytes for every packet, or the the length is such that the maximum amount of data that is possible to be encapsulated in a single packet, that HTTP data you start with, that is 1500 byte, something between among these two. Okay. So in this way, encapsulation happens automatically and your stuff starts getting longer and longer and longer. So next is we'll just take a short break, then we'll come back, we'll discuss what is the mechanism of accessing a page at say www.google.com. Okay, so that will give you an idea of the details. Thank you. We'll be back. It's 9:31. We'll be back in 5 minutes. Okay, welcome back. So just a few clarifications. As I was saying that this MAC address example, it showed 64-bit. 64-bit MAC address is actually a newer version of the MAC addressing. This is followed in some niche application areas and wireless ad hoc wireless network kind of domains, and also it is proposed to be used when fully IPv6 with 64-bit IP addresses, 128-bit IP addresses become common. But right now, most of our devices which connect to either Ethernet or to wireless, they use 48-bit MAC addresses. So there will be 48 identity. I mean, one here it shows 8 bytes. There will be 6 bytes. Secondly, the names of these data packets at different layers. At transport layer, it is called a segment. At the network layer, okay, so you should kind of memorize this. Transport layer is segment. Network layer is datagram or packets. The packet terminology is confusing. It is, some people want to use it for transport layer segment. Some people want to use it for network layer datagrams. So if you want to be absolutely error free, don't use the term packet and use transport segment and datagram for transport and network. And data link layer, it is called a frame, the entire encapsulated stuff. Please understand that what I am talking about is the complete stuff, like the transport layer segment consists of your HTTP data along with the HTTP header, along with the TCP header. Together is transport segment. Okay, not that the HTTP data only is the transport segment. That's not the case. Now, physical layers, there I don't think there is any separate name, just that because they have at the bottommost layer, they have become bit level stuff. With the trailer and headers. You can still call them frames if you want. Now, to get an idea of how much restriction the physical layer imposes on the other layers, just to give you an example, theoretically, the network layer datagrams, the total length of the network layer datagrams can be up to 64 kilobyte, which is over 65,000 bytes. However, because of the severe restriction placed by the physical layer, in most cases, many cases, the network layers datagrams are forced to be about 1400 bytes. Just imagine 65,000 bytes is allowed, but you will be forced to only send out data packets of size, total size around 1400 bytes, which is quite bad because you could have sent out larger HTTP data in one datagram. Now you would not be able to do it. You will need to break them up into small chunks of 1400 byte and send out so many different datagrams. But unfortunately, that is the situation. And since there is a strict, there is a strictly increasing order of the lengths as you go down, so your application layer packets would also be of certain size. So basically your HTTP data will be much lesser than 1400 byte, probably something like 1200, 1300 or 1100 bytes, means we are coming down to about 10 kilobyte of user data being transmitted every datagram. Whereas every datagram theoretically is about 64 kilobyte. So from 64, we have come down to 10. Oh no, so not even 10, sorry, 1 kilobyte. 1024 is 1 kilobyte. So from 64, I have come down to 1 kilobyte, a factor of like over 60 decrease. Okay, so this is what happens. Now let's just see very quickly. We will study this in some detail later on when we study HTTP. How do you access a page at google.com? You type the www.google.com in your browser address bar and press an enter. First, your computer contacts something called DNS. Okay, the application layer. It uses something called DNS to get the IP address of the Google server. This IP address is required even at the transport layer. Okay. Although the IP address is actually a network layer identifier, it is required even at the transport layer. This DNS is a service which returns that the IP address of the Google server you are looking for is this 74.125.224.72. It requires some time, but typically not much time. Typically within 1 or 2 seconds, less than 1 second, it will return. Then the application constructs an HTTP GET request. All of these things, what is DNS? What is a HTTP GET request? All of this we will study. Okay, so don't worry. Next week we'll cover all of this. So then it constructs a command like get this / index.html http /1.1. What is the meaning? We will study. Essentially, it is saying that get the file index.html from the machine with IP address 74.125.224.72 and HTTP version 1.1 is being used. It constructs an HTTP packet and forwards it to the transport layer. The HTTP packet has certain format and it is forwarded to the transport layer. Then in the transport layer, it constructs a transport layer packet or TCP segment, we should say. Let us use the term segment, okay, not TCP packet. Now, there is a source port, which is a port address corresponding to your browser tab, that process that is now identified by process identified by the operating system, but it is also identified by a source port for that connection in the transport layer. Say the source port is 3324. The source port typically is a numbers above 1024 and less than 65,000 typically from your browsers, etc. However, the destination port, if you want to use HTTP, must be 8080. That is fixed. There is no change to this. So the destination port, if you want to use a HTTP request, must be 80. Okay. So you source and destination port you note down. There is a sequence number, acknowledgement number. What is the meaning of this? What is the meaning of all these fields that are shown? Is there checksum, urgent pointer, options, padding, all these things are there. Finally, there is the data of what you want to send that begins. The network layer takes that transport layer segment and constructs a network layer datagram. See, every time this packet terminology is being used across all the layers, application layer packet, transport layer packet, network layer packet. So this packet is the most common terminology, but there are differences between them. Now it says that the source IP address of your machine is 172.16.22.121. It has started with 172 because probably it is inside a larger LAN managed by a large institution like IIT or maybe some office. Okay. Anyway, so that is currently the IP of your machine, and the destination IP is just the next hop IP for this. Okay. How will you know what is the next hop IP? For 74.125.224.72, that is the Google server. Well, you will use a procedure called routing, which is slightly complicated actually. Later on, we'll find to get this IP. Okay, so those will be noted down: source address, destination address, etc., etc., and these options, padding, etc. Everything options will be given along with padding, and then data. Everything will be given. The width of this will be 32 bits. Different fields are always either they're all in bytes, different byte sized fields. Okay, all of these again that at packet format we will study in detail. Then the network layer from the router, it uses the routing procedure to find out the next hop to reach the Google server at this. As I said, that let this IP address be 172.16.28.192, which is another router to which your packet will be sent. Finally, after the routing procedure is over, there are many steps. Over many hops, this will happen. Then finally, when you reach a page at www.google.com, the data link layer takes the packet from the gateway router, the router at the interface of their office. Okay, and through switches, finally it makes the connection to the machine to which it has to be connected, which is 172.16.22.121. All the switches, the gateway router, and the server to which finally connection is happening constitute the local area network or the LAN. Okay. Now, these frames also have a particular format. There is a preamble, destination address, source address, type field, data, CRC, polynomial, check, 4-byte polynomial check data to check that everything, data is not corrupted, etc. All of these details also again we will learn. Okay. Now it needs the MAC address actually to get the to deliver the data. So it will use a protocol called ARP to get the address resolution protocol to get the MAC address corresponding to the IP address 172.16.28.192. I think here it won't be 192, it would probably be 121. 28.121 because that is the final destination of the packet. Okay, so in summary, as we said, that your user data actually constitutes a small part of the entire segments, and later on the datagrams and the packet and the frames. Okay, all of this continuously keep on adding extra information to make them longer and finally pushes it onto the physical layer, which actually delivers the frame electrically in terms of bit patterns. Okay, so next week we will study, next Monday, this essentially we will study the DNS mechanism. You know, this first step of how to get an IP address corresponding to a text string like www.google.com. What is the mechanism that supports it? So once you understand that, a major mystery will be solved for you, for those of you who don't know, because this is really mysterious, right? If I am saying that the identifiers are addresses called IP addresses, which are 32-bit numbers, how on earth do I type a numeric a string like www.google.com and still get connected to the address? So that we will study. Thank you. Please read either Tannenbaum or either of the two textbooks, either Tannenbaum or Kuros and Ross, to understand the basics. Probably for this section and the application layer, you should try to read Kuros and Ross because that is better described there. Thank you.
Thank you, sir.